Y'all are killing me. Would f of x equal 5? F of x equals 5 to the x look familiar to you if you did your homework last night? Yes. F of x equals 1/2 to the x. So b is just some number. You did those last night. Okay? Now, f of x is really a y. So could we not rewrite f of x equals b to the x as y equals b to the x? Yes. Now we're finding the inverse. It says all exponential functions have inverses. So how do we find the inverse? That's step 2. We switch the x and the y. I've done that for you. Okay? And then we solve for y. We've done this. This is how you find the inverse of a function. You take the x and the y, you swap the x and the y, you solve for y. But we have never solved anything like step 2, x equals b to the y. We've never done that before. We never solved for a y that is in what spot? The exponent spot. We have never done that before. That's because it takes logs to solve sometimes for a variable that is in the exponent spot. And I probably wrote that down. To solve for the exponent, a new notation called log notation is needed. Okay? Sometimes it's needed. Sometimes you can do it with the exponents, and we'll figure that out. Okay? This notation, this log notation, gives us a way to name the inverse of f of x equals b to the y. The inverse function of the exponential function with base b is called the log function with base b. If you have taken the ACT before and you have seen some log problems pop up, you're like, what in the world are these? Okay? They are not that hard. It's just something that you don't learn until you get to Algebra II. Okay? So here's the definition. It's much easier than what you're thinking right now because I've been making you read all the definitions. The definition of a log says if x is greater than 0 and b is greater than 0 and b is not equal to 1, then y equals, this is log form right here. This is called log form. Y equals log base b, the little subscript is your base of x. I'm going to read that again. Y equals log base b of x. That's log form, is equal to b to the y equals x, which is exponential form, something that you're familiar with. B to the y equals x is exponential form. You're familiar with that. You're not familiar with the log form. Okay, they are equal to each other. One is log form, one is exponential form. So first thing we're going to do is we're going to practice going from one form to the other. Okay, and because I was just in John Baylor Prep, Mr. John Baylor Prep, does he have a name, Natalie? Did he ever tell you his name? The guy?
John Baylor.
John Baylor? You think he is John Baylor? We're just assuming. Haven't really thought about it. Okay?
On the first day he said, I'm John.
He's John. Okay, well then that is John Baylor. That makes a lot of sense, doesn't it? He had the, let's see if Natalie remembers the technique here. Starts with an S. P. I. Anybody else in John Baylor? You didn't go this morning, did you? You go this afternoon. Did you go this morning? No? The spiral technique. Okay? Remember that now? Okay, so you take the subscript. An example 1, what is a subscript? What number represents the subscript in that?
5.
The 5. Okay? And you do a little spiral towards the equal sign. And then you go back around and you end up with the x. So 5 is your base. The subscript is always your base. Then you do a spiral and you loop back around. 5 to the second power is equal to, and then you end up with x. All we're doing right now, taking it step by step, because we're still in high school, we've got this log form, and the directions are asking us to write it in exponential form. So you start with a little number called the subscript, and you do this spiral, his spiral technique, and you go 5 to the second power is equal to x. Do the same thing for 2. We're not solving anything yet. We're taking this step by step. What's the base? Number 2, example 2, what's the base? B, and you do the spiral technique. B to the third is equal to, and you end up with 64. That's all you're doing there. Example 3, what is the base? 3, do the spiral technique. B to the, you go across the equal sign, so this time we got to go to the right. B to the x is equal to 7. All we're doing here is writing the log form into exponential form. Sometimes that's helpful. If we can get it in exponential form, it's going to be easier to solve than log form. because we're more familiar with exponential form, makes a little bit more sense. Okay, so all you're doing on the first part of your homework is write each equation in equivalent exponential form. So it's the subscript as your base, go across the equal sign to your exponent, and you end up with the other number. 5 squared equals x, b cubed equals 64, 3 to the x equals 7. Any questions about those? All right, now they're going to make us go the other way. It says write each equation in equivalent log form. Okay, so now we're going backwards here. So let's start with the word log, L-O-G. And then you do your little subscript. And your subscript is your base. So what's the base of 12 to the second equals x? 12. Okay? And then the next number is what your 12 squared is equal to. That's going to be x. And I always like to say logs are equal to exponents. Logs are equal to exponents. So log base 12 of x is going to be equal to 2. Logs are equal to exponents. Example 5. Log, what is your base? B. So that's a little b. Okay, log base b of 8 is equal to the exponent 3. Example 6. Log base e of 9 is equal to the exponent y. So now we're going from exponential form to log form. Log form's our new language. It's like we're going from one language to another. Okay? Next set of directions are going to tell you to evaluate. Next set of directions are going to tell you to evaluate. Evaluate means work out until you get one answer. Evaluate means work out until you get one answer. So we're looking for x. We're actually looking for x. I don't have an x here, but if it helps you, you can write equals x on each one of these. So that we're looking for what log base 2 of 16 is equal to. So if we're looking for something, we put a variable there. So log base 2 of 16 is equal to x. We do the spiral technique, and we rewrite it in exponential form. So what's the base? 2 to the x is equal to 16. And take a look at that equation. That should make a little bit more sense. So they're asking us 2 to what power or what exponent is equal to 16. You should be able to do that in your head. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. So your answer would be 4. X is equal to 4. Now some of you, once you figure out what we're doing, you would do example 7 without any work at all. So let me go back and show you example 7. If we didn't have any work, we know our base is what? 2. We know our answer is 16, but we're looking for the exponent there. So 2 to what power is 16, and that would be 4. I don't care how you do it. Once you figure out what you're doing, you're probably going to be able to do these without any work. If you get confused, then do the work. Okay? I'm going to show you the work on all these. If you can skip the work, that's up to you. So example 8, we're evaluating log base 7 of 1 over 49. So we're going to set that equal to x. We're going to do the spiral technique and rewrite this log equation into exponential form. So that's going to be 7 to the x is equal to 1 over 49. Now this one always throws some people off track here. We need to get both sides in the same base. If you can't just see the answer, and I know there's some people out there that may know what the answer is. Anybody know what you can raise 7 to get 1 over 49? Negative 2. Good. Okay? Does everybody get that or not get that? If it were 49, you could tell me x was positive 2, right? But because it's 1 over 49, that's why it has to be a negative 2. All right, example 9. Set that equal to x. Base is 25. Do the spiral technique. 25 to the x is equal to 5. 25 to the x. 25 is smaller than 5. 25 to the first power is 25. 25 to the second power is 625. What are y'all thinking?
1/5.
Can't be a whole number, can it? We just did 25 to the first and 25 to the second. That's not going to give you 5. It's going to be a fraction. Mary Frances says it's going to be 1/2. Why does that make sense? What does to the 1/2 mean? Let's put it back in there and see if it makes sense. What's to the 1/2 mean?
You take the square root.
It's the square root. If your exponent is a fraction, the bottom number is your root. If the exponent is a fraction, the bottom number is the root. All right, example 10. Set it equal to x. 2 to the x is equal to the 5th root of 2. Again, if you can do this without any work, you can do it without any work. You're looking for what exponent that you can raise 2 to that's going to give you the 5th root of 2. If it's more confusing, write it out like I've written it out. What's the exponent on your 2 that would give you the 5th root of 2? 5 over 2. 1/5. Okay? Y'all remember if you have the 5th root of 2 to the 1, 1 is the top of the exponent and 5 is the bottom. How many got lost on example 10? Okay? All right, let me show you this step. All right, so if we left the left-hand side the same, could you rewrite the radical, the 5th root of 2? Does it make sense to put this step in? Y'all remember us doing exponents that were fractions? Okay, radicals and logs do not get along. Radical symbols and logs do not get along because logs are equal to exponents. So sometimes you want to change your radical either in your head or on your paper. You want to change your radical symbol to an exponent that is a fraction. Now does the problem make sense? 2 to what power is equal to 2 to the 1/5? And that's why the answer is 1/5. Okay? All right, example 11. Let's see if we can do this one without any work. Example 11 says the base is 4. So it says 4 to what power is equal to 4 to the 6th? 6. 4 to what power is equal to 4 to the 6th? This is an example of when the two bases are the same. The base on your log is 4, and the base of the value after that is 4. And when that happens, the logs really just cancel. The 4s just cancel each other out because the bases are the same. Okay, we're going to do that in example 12. My big base is 7, and then the base of the log is 7. Kind of looks like an N. The big base is 7. The base in the log is 7. When the bases are the same, they cancel each other out, and the answer is just 23. So on 11 and 12, I would do those without any work.
Can you explain the last one?
If the bases are the same, they cancel each other out. Whatever number's left in the problem is the answer. If the bases are the same. So like in example 11, the base on your log is 4. The base of the next number is 4. Those cancel out. The answer is 6. Yes?
On our homework, will we have an example where it's written like number 12, but they don't cancel each other out?
No. They're going to cancel each other out every single time. Okay? Because you're not going to get to the really, really hard ones. They're going to have the same base. That's why they're giving you those, to make sure that you know that they cancel out and you're left with whatever number's there. All right? So do you have to show work for these? No. If you need to show work, you can show work. We've done some with work. We've done some without work. That's up to you. All right, example 13. Is this the last example? Yes. It says graph f of x equals 5 to the x. We did that in our homework last night. And we have to graph a log. We've never graphed a log before, but we're going to figure out how to do that together in the same rectangular coordinate plane. So we're going to graph f of x and g of x in the same coordinate plane. So let's start with f of x. Let's start with f of x. So f of x equals 5 to the x. How can I graph that? What do I need to graph? Okay, I can graph 0 and 1. So when x is 0, y is 1. When x is 1, y is 5. Where's the asymptote of f of x equals 5 to the x? At y equals 0. All right, so the first part we totally know how to do. Totally know how to do the first part. We've already done that. That's why we have to do exponential functions before we do log functions. Now, in all those directions I was reading to you, I said something and you probably didn't even catch it, but it said exponential and log functions are inverses of each other. Exponential functions and log functions are inverses of each other. So we're about to graph log base 5, which is going to be an inverse of 5 to the x, because they have the same bases, right? One's in log form, one's in exponential form. So when we graph, we like to find x's and y. So I want you to take your log function. You take your log function, g of x equals log base 5 of x. And because we like to find x's and y's, let's change g of x to what? A y. Let's change that to a y. And then we don't like to graph in log form, so let's rewrite this in exponential form. We do not like to graph in log form. It's too complicated. So let's rewrite it in exponential form. So let's do the spiral technique. Our base would be 5. Our exponent would be y. And 5 to the y would be equal to x. Okay? Once we get into exponential form, then we'll make a t-chart. And then something should feel strange. Anybody feel the strangeness? What's weird about this? 2 variables. What else? The y is the exponent. What is usually the exponent when we go to graph? The x. So we can't pick x's here because x is not the exponent. We have to pick y's. So let's pick y is 0 and y is 1. That goes totally against what we have always done. We usually pick x's, but we can't pick x's here because the x is not in the exponent spot. The y is. So when y is 0, what is x? 1. When y is 1, what is x? 5. Take a look at your 2 t-charts. Opposites. Opposites or inverses. Aren't those points inverses? Yeah, they need to be inverses because your graph have to be inverses. So when we go and graph our log graph, we're not going to graph 0, 1. We're going to graph 1, 0. Okay? Some of you will go, well, I'm not even going to do all that, change into exponential form. I'm just going to take my original t-chart and swap the x's and the y's. You can do that too. Okay? But you have to know logs are inverses of exponential functions to know the shortcut there. So let's graph our new log. We've never graphed logs before. I'm so excited about this. We've got 1, 0, and we've got 5, 1. We've got 1, 0, and we've got 5, 1. Also in all those words that I put on your notes, it said that inverses are reflections over the line y is equal to x. Inverses are reflections over the line y equals x. How do I graph the line y equals x? What's the y-intercept of y equals x? 0. What's the slope of y equals x? 1. So is y equals x not this imaginary line that I'm sketching in? Is that not the line y equals x? Slope is 1, y-intercept is 0. This kind of helps you just a little bit because you've never graphed a log graph. So your f of x and your g of x should be reflections over that line. So could you sketch in your graph now? Where's the asymptote going to be? Okay, let's say you just don't know. You're just going to watch me. Bless you. To me, even drawing that log graph, just kind of, it's like I'm writing with the opposite hand. Because we've done all these exponentials that are growth and decay. When you swap and you graph a log graph, to me, it's like you're graphing with the wrong hand. Okay, but sometimes drawing in that reflection line, do you see now how the green line can be, the green graph can be folded over that y equals x line and you get the blue graph? The blue graph can be folded over the line y equals x and you get the green graph. So log functions do not have horizontal asymptotes, they have vertical asymptotes. Okay? That slanted line is just a line of reflection. You don't have to graph that line, but you're just learning how to graph logs, so it might be helpful for you to dash in the line y equals x. So log functions are going to have vertical asymptotes, where exponential functions are going to have horizontal asymptotes. Why does that make sense? Exponential functions have horizontal asymptotes, log functions have vertical asymptotes. Because they're inverses. So everything that would happen with the x now happens with the y, and everything that happens with the y now happens with the x. So the last part of your homework, you're going to graph an exponential function, and you're going to graph its inverse, which would be its log function, on the same graph, and example 13 will help you do that. Any questions about your notes? All right.